the school has la presentazione is in inglese, because no hablo español. Just to start here, a few words on actually, last year I was at the Department of Aeronautical Engineering, and now I'm at the School of Aerospace Engineering. This happened last year in the middle of the year. Then a few words on, in order, before to start talking about fires, prevention, detection, damage assessment, let me introduce a little bit the place where I'm working, the school. The Aerospace Engineering School is a school that is providing a post-degree that can be accessed by students that already have a master's degree. The school, and of course the area is the aerospace engineering. The students that have already a degree in aeronautics or aerospace can take the degree, the school degree in 1 year, otherwise they have to do the courses made of 2 years. The most important fact is that, okay, all the courses are in English, and the most important fact is that any professor of the school has a lab. So the students will be, they have a theoretical part, but mostly a practical part. So the idea of the school is that preparing the student to access the farms or industries in the right way, to help them and find a job more easily. So just a few words on the school. The school actually, possibly you know that Italy was the 3rd country to send a satellite into space. This was due to the University of Roma, and in particular to the School of Aerospace Engineering. The school launched the first satellite in '64, then just after the Russian in '57 and the US in '61. And the satellite series was called San Marco. This was really the history. The launch were made from a platform at the equatorial area in front of the coast of Guinea. But going a little bit more near today, in '97 the school started with this project of a small satellite called UBSAT. After that, after the 2010, they started with a new program. We started with a new program that is based mostly on CubeSat. So from then, we at school were developing several CubeSats. CubeSats are all of them made by the students. So the students during the course, they are participating in building the CubeSat that is at the end of the study, they will be able to send this to launch this small satellite, and so checking their ability in doing something that at the end is able to provide information. So in fact at the school we all the professors in this case have developed some onboard computer for CubeSat, already tested on a couple of satellites or CubeSat. The last one was launched a couple of years ago. It was in cooperation with students coming from Iraq. This was a project of the Ministry of Foreign Affairs in Italy. Students from Iraq came in Italy for 2 years. At the end of the 2 years, they built and launched this CubeSat devoted to monitor the dust storm that of course is a problem in the Middle East area. We have also some facilities that, for instance, there is a room that is devoted to simulating the lunar area. So this is made for studying rover system capable of moving in an autonomous way on the moon surface. And also other systems like this for analyzing or developing algorithms for controlling the dock among two satellites or among two systems in space. And concerning myself, the activity concerning remote sensing started more or less around the 97, because in Kenya, from where this station that we have since 63, devoted to launch small satellite, we have also antennas for receiving satellite images. At that time I was responsible for this station, so made of several antennas. Actually, from the station we are doing the reception of images, satellite images, as well we were doing some activity concerning the support of satellite launch from the French Guyana rocket launch, rocket range, and also launch made by Boeing or other companies. On the basis of that, starting from that images, we started to develop several different applications. Of course, we are doing a field campaign quite often in the Kenya region, because we have a strong relationship with this country due to the agreement and the relationship between Italy and that country. And okay, but let's go to the problem. Using satellite for managing forest fires. So from the point of view of management of forest fires, we can consider three phases in the management of the fire management. The prevention phase, the detection, monitoring phase, and the damage assessment and the recovery phase. In the case of the prevention phase, we have developed several applications, for instance, for providing fuel map, hazard map, and also this fuel reduction map, that is a map that provides an idea of the area where removing the fuel can be convenient, can help in reducing the risk of fire. Concerning the detection, we have developed a system, a processing chain, that is providing forest fire monitoring mostly based on the geospatial satellite. So this gives us the possibility to collect, to observe, to have an image of the Earth every 15, or actually in the case of Europe, every 5 minutes. So every 5 minutes we have an image of the surface, of the Earth's surface, then we can have every 5 minutes of information of the presence or not of the fire in the area of interest. And other things are coming from that. Concerning the final point of the recovery, we have developed, of course, in cooperation with partners in several projects, algorithm or technique for assessing or defining the environment area, as well for estimating the damage caused by the fires on the vegetation, of course, in this case. So let us go to the first point. This I'm just repeating what I said before. So this presentation is mostly devoted to presenting some of these products that we have developed in years, several years, concerning that can support the management of forest fires. Starting from prevention, so from the point of prevention, we have developed maps or products that are provided with different times, with different figures. For instance, full map or vulnerability map are provided every year. So every year at the starting of fire season, these maps are provided for to be used in, from others applications. There are other products that are provided seasonally. Seasonally, in this case, it's every 2 or 4 weeks, with a frequency of 2 or 4 weeks during the season, the fire season. That in Italy is from June to the end of September or October. This is the case of the risk map and the so-called hazard map. And finally, concerning the prevention, we have developed also one of these product called the Daily Fire Hazard Index that are provided daily during the fire season. This is the case of the Daily Hazard Index and Prescribed Fire Index. I do not give fuoco prescritto is something that is made in Argentina, or possibly all the products, of course, the products are connected each to the other. For instance, in this case, all of them needs the fuel map. So the fuel map is a map providing an idea of the capability of vegetation to support the fire. So in this particular application, we used rapid eye, different kind of images, rapid eye, spot, Landsat, and also noise. Starting from the fuel map, this is an example of a fuel map for a small region of the Spain, because most of these things that I'm presenting here are the product results of a European project funded by the European Commission, in which Spain, Greece, and Portugal, and France, and Italy was very involved. So most of the products were produced for these countries, of course. That is an example of one of these fuel map. Characteristic of this map, the resolution is going from 5 meters to 30 meters. It depends on the area of interest. If the area of interest is, for instance, a protected area, so not a large area, this kind of map can be done at a resolution of 5 meters, otherwise it will become too expensive. For a big area like a region on opposite, in that case you don't need so high resolution image. In that case, the resolution would be 30 meters. How this one is produced and what means fuel map. As I said before, fuel map means that is representing the characteristics of the vegetation with respect to the fires, how the vegetation responds to the fire. In Europe, in several years, we developed at the end, because since 72, US they developed the fuel type, list of fuel type. At the end, in around 2005, 2010, Europe, starting from these maps, these fuel types defined in the US, defined the fuel maps, fuel types used for Europe, for the European vegetation. So there are reported the different fuel types of this model developed by the GRC, that is a Joint Research Center, that is an European center devoted to produce things for Europe. What does mean fuel map? Fuel type means that for any kind of vegetation type are provided information concerning the amount of live vegetation in the corresponding to that kind of vegetation, the amount of died vegetation, the minimum of the moisture in the plant needed to burn, or up to which the plant will not burn, and also it can also provide some more information concerning the so-called, for instance, ROS, so the rate of speed of the a fire if that kind of vegetation is interested by a fire. So this kind of characteristics are provided for each one of the different vegetation type. As I said before, this kind of map were developed as several projects, starting from that one called the fuel map. In that project, the vegetation type, the fuel type for Europe were developed. So something different from the basic fuel types developed in the US from Anderson, Google, and other people.
The second one, the Arc Fuel project, provided a methodology for extracting the fuel map from satellite images. And finally, we used this methodology, the fuel type developed in the other project, in this other project called PREFER. So in PREFER, using the information provided by other previous projects, we developed our methodology for producing our maps. Just to few words, the maps are based on, in particular, up to now in Landsat, are made using Landsat in the case of, let me say, high resolution images, high resolution product, or Rapid Eye when we are interested in a very high resolution map. The approach is based on multi-temporal, is a multi-temporal approach, so images acquired in different periods of the year are used. And also, since of course the capability to fire the area to support the fire depends on the amount of the vegetation, of course, in the area. It was developed this methodology to extract the so-called vegetation fire fraction or vegetation fraction cover. So we are talking in this case of satellite images, means that we are talking about pixels. So this was just a method to extract the fraction of the pixel covered by vegetation. So the relationship is quite easy. They are defining a vegetation in so-called NDVI. NDVI is an index commonly used for, let me say, in a certain sense, measuring the amount of vegetation in a pixel. Higher the values of this NDVI, higher the amount of biomass of vegetation in the pixel. So they just define an NDVI for a vegetated area, another one for the bare soil or for soil. Then from that, the fraction of vegetation present in the pixel can be measured. In this case, this NDVI is the value, the actual value measured by the satellite on that pixel. The other values needed are defined in this table given by that project. So this was the fuel map. Using a fuel map and using other information, we can develop, this is what is called the seasonal fire hazard map. In this particular case, the seasonal fire hazard map that has a resolution of 250 meters in this case, because in Italy, in most of the countries in Europe, at the starting the season, for instance in June, the civil protection is providing the regional authorities with a map that is called risk map. So that map is given in June, is the same for all the season. So we are trying to do something that can be changed during the season, because the map that they are providing in June is a map that takes into account what is the occurrences of fires in the previous 10 years, for instance. Then it's just based on a statistical analysis. But we try to change this, trying to introduce the actual meteorological conditions for the actual season, as well also the actual behavior of the human, of the people, persons in the present year, because mostly, at least in Italy, 90-95% of the fires are due to the human intervention, so are persons that put fires for many different reasons. So we developed this method in which we are taking account, for instance, the fires occurrences in 15 days, 2 weeks, and also the meteorological conditions occurred in 2 weeks, in order to modify this hazard map provided at the starting of the season. So in this way, introducing the fires occurred in the previous week, we are just taking into account the human factor. So this is one of the main points, because for instance, in Italy, but everywhere, if no one is putting, okay, you have the case of the lights. I think it was the reason of the big fires that you had in the south of Argentina this year. But in Italy, everyone, the condition can be very high temperature, dry weather, but if no one is putting a fire, the fire will never start. So the human being is very important in this case. Then in this way, we can in some way take into account the human behavior for that particular year. Another important aspect that gives, because the risk is defined as the product, is generally defined as the product between vulnerability and hazard. So up to now we saw the hazard. In order to have the risk, we have to define the vulnerability. The vulnerability was computed considering several terms. One is the exposure, so the characteristics of for instance, the buildings or other infrastructure that are exposed to the risk of burning. Then, for instance, the population, buildings, road, and so on. Then the sensitivity. The sensitivity of these elements. Sensitivity means also the presence or not of schools or others, I don't know, hospitals or other things like this. Then the so-called coping capability, the capability of the authorities in the area to intervene in order to contrast the fires. And finally, the economic value, so the relevance of the area. So combining all these terms, we come out with this. On this, there is also, if someone is interested, there is also a paper that I can address to you. I can tell you which one, where all the methodology is described. So the resolution in this case of the product of the map is around 100 meters. The area there is a province of Portugal, north of Portugal. Then, combining the hazard map with that vulnerability map, we can come out with this risk map. So the risk map at the end is a map providing where we have just 5 colors. Each one is associated with a different level of risk, from low to maximum. The last one, not the last one, another one of the product in this part of the prevention is this one, what we call daily fire hazard index. This is based on, the resolution is 250 meters. More or less here are reported all the data that we need. So we are using a digital elevation model, this particular case, the one provided by the SRTM, the mission. Then we are using the fuel map, meteorological data, temperature, humidity, and wind. Then satellite images, MODIS in this case. Using satellite images, we are producing an NDVI, and also this other index called EWT, equivalent water thickness. The equivalent water thickness is used for estimating in some way the water in the plant, so the moisture in the plant. Using them, we put them together, or combine them in some way with some algorithms, come out with our map. There is an example of these maps from the 1st of August to the 31st of August. So the light parts are the part where the risk is higher. So you can see how the risk is moving day by day around the island. This was the Sardinia region. Okay, this was August of the last year. I want to say something. I cannot recall. Okay. Okay, sorry, I cannot recall what was... sorry, ecco, we are producing this for the present day, for tomorrow, and the day after tomorrow, because the meteorological data were available for today, tomorrow, the day after tomorrow. But if, for instance, we have meteorological data for 1 week, as usually meteorological system centers are providing, we can provide this map for the seven days. So you have a projection of the risk, hazard, then probability of fires from now to the next 6-7 days. This is just for describing the methodology related to this daily fire hazard. Then we download automatically the MODIS images. Since this is made daily, we cannot have one people that's staying there downloading manually the image. Of course, this is made automatically, but not from an antenna. It's made automatically from the USGS website, the site where all the MODIS images are available, with an FTP request. Then we compute this NDVI, these two indices. We combine from that indices, we compute a index called the relative greenness index. On the other side, we have a digital elevation model and fuel map, and then combine all of them, we can estimate this, we can produce these maps. This map was an evolution from, because initially, the idea is based on what was developed in '98 from this, from Burgan, this US scientist, he called it FPI, Fire Potential Index, the index developed using satellite images. Then there was some improvement in order to transform this index in something that can be used in Europe. At the end, we did some more, we introduced some changes. One was the illumination, the solar illumination, the introduction of the solar illumination, because of course there is difference between vegetation illuminated by the sun with respect to the other side of the mountain, of course, for instance. Then we introduced a way to take into account this. As well, we introduced this new term that we call the equivalent water thickness, that was devoted to try to estimate the water in the vegetation that can reduce the capability of the vegetation to burn. Okay, leave the relationship. Okay, some equations were used for this. Now, another, in some region, also some country in Europe, is possible to do this, is called prescribed fire. So, fuoco prescritto, I think that is, in Spanish is the same, sarà fuego prescritto. Prescribed fires means that you can remove some vegetation using fires. This, of course, should be done in some period, for instance, the winter time, when the risk of producing a big fire is reduced. So we have developed this prescribed fire, but since the idea was to produce this prescribed fire map, but since in some other regions in Italy, you cannot do this technique, you cannot use the technique of prescribed fires for removing the fuel, we developed what is called this fuel reduction map. Let me... So the fuel reduction map is taking into account parameters like the elevation of the area of interest, the slope and the aspect, also of course the fuel type, the climate, and then combining all of them together, we develop what is called homogeneous territorial classes, so classes of territorium with the same characteristics. Then combining these classes with burned area, taking into account, for instance, the burned fires events occurred in the last 8 or 10 years, we can develop this map that we can call fire propagation probability map, or combining these maps with buffer zone around the area of interest, then, for instance, around the roads or parks or protected area, we can define a map of the area where the fuel should be reduced in order to reduce the risk of a big fire, so very dangerous fire. Then this first map provides us, this first map, what I call it the fire reduction map, provide the place where the fuel should be removed, or it's better if you remove the fuel. You can remove the fuel in different ways, using fire, using mechanical system, any other system. The map is combining this map with, as I said before, with this buffer zone. We have some area there where in red are the areas that deserve a major attention in removing the fuel, where it's better if you remove the fuel in order to avoid big fires. Now, combining that map with some, in Europe, there was a project that was called Fire Paradox that provided the information or all the constraints for applying this technique called prescribed fires. In particular, in order to apply you can apply this technique of removing the fuel, then the prescribed fire technique, for instance, in the winter time. This is the case of Sardinia. Winter times, the wind should be from 2 to 8 kilometers per hour. Humidity should be around 40%, the temperature from 6 to 15 degrees, and so on. Then, combining the previous one, the fuel reduction map, with these conditions, we can have what we call prescribed fires map. So a map, let me go back. A map, I don't know if it's, you can see, a map where we have the places and the time when you can apply the prescribed fires. For in this case, was red means today. Today, the area where you can apply the prescribed fires is the one in red. Tomorrow, the one in green. The day after tomorrow, this small area in blue. So this was just the area where you have the meteorological condition right for applying the prescribed map, the prescribed fire technique. Of course, using this technique, you can also develop something like this. So this map is providing, during the season, how many days in any pixel have the right condition for applying the prescribed fires. The prescribed fire method. As you can see, we have area, for instance, this in blue, or other in black, more or less, or dark blue. That means that during all the season, you have just 1 or 2 days that the meteorological conditions are satisfied. So this means that in that area, you cannot think to apply the prescribed fire technique, but if you want to remove the fuel, you have to use other techniques, mechanical methods or other methods. Okay, let us move on the last part, the path of recovery, the damage assessment. So I leave for the end the part concerning the detection and monitoring of the fire. Concerning the recovery, also in this case, the products produced are given with different frequency. For instance, this one concerning the soil erosion susceptibility map or post-fire vegetation recovery map are given twice per year. Other, like the burn scar map, then the estimation of the burned area, or also the damage severity maps are provided every 2 weeks. Why every 2 weeks? Because in this case, since this was last year, the images from the European satellite Sentinel-2 were still not available with the right frequency. With the we were using Lancet. Since Lancet has a revisit frequency of 16 days, okay, now we have 8 days because, but we are not using Lancet 7 because, I mean, for the noise in the image. We have the frequency of 16 days. And this just comes from the fact that we are using Lancet. Then, if there is a fire in a certain area, we have to wait 16 days in order to have another image of that area detect the fire, for detecting the fire. In this case, all the products are starting from the burned area. Then, first of all, in the project, the first product, or most important, was the delineation of the burned area, then the detection of the burned area. All these different products were developed using different kind of satellites, as you can see, from high resolution or very high resolution, rapid eye, spot, Pleiad, so resolution of 1 meter or less to 30 meters, also some radar images. Okay, this is an example of this burned area. The resolution, as I said before, is of the order of 30 meters. This can be detected, is not needed that we have, for instance, we have an image of the area given by the spot satellite. We don't need to have, after the event, an image of spot. We can have another kind. So we can put together images coming from different satellites, not necessarily from the same. Anyway, this is an example using Lancet images. Okay, this is a description of the methodology, but let me, we can avoid this. Just in general, so the images should be, of course, given by satellite that have a green channel, red channel, near infrared, a SWIR channel. We need these 4 channels in order to assess, to estimate the burned area. In my opinion, this is one of the most interesting products because you can have, every 2 weeks, you can have the distribution of the burned area in the region of interest without much effort, just 2 images. But in some cases, this was also the case in Italy, when we showed this to the authorities involved in doing this activity of defining the burned area, because in Italy there is a law that requests to all the region and the province to provide information of the burned area. They said, but no, we don't need this. We can send the people to do this. So they, instead of being in the office, they can go around doing these measurements. So, but this seems not, in my opinion, not a good approach to the. Anyway, there are many different ideas about the thing. So something that seems very useful for other people, not so useful. But so this is just a comparison between, because there is a European project that is called EFIS, European Forest Fires Information System, made by this JRC, this Joint Research Center, that they also have, they are providing also this burned area map. But they are doing this using MODIS images, so 250 meter spatial resolution. What is the results is shown here. In red, in black, we have the fires detected by the burned areas detected by this EFIS, and in red, those detected by the burned scar or the meteor developed in the PREFER. As you can see, in this particular case, of all the fires, EFIS is able to detect just 4. Instead of more or less there will be 50, something like this. Because since he's using MODIS, he can detect fires of a size larger than 12 hectares, from 12 to 20 hectares or larger. So in using Landsat, you can detect fires of the order of less than 1 hectare. Okay, this is just an example. This is the image preview. The image, sorry, from the, here it seems similar, so nothing. But anyway, this is the previous, this is the image after the event. Unfortunately, it's not well, cannot be seen well. Okay, let me, this was just a comparison between what was done using our approach and the one using, made by this EFIS-based approach. But sorry, it's not. There was the yellow line is the one produced by preferred by our project. It should be a black line here that I think you cannot see. That's showing the results given by the other project called EFIS, this other system called EFIS. Of course, if someone is interested, also very high resolution images can be used in order to have a delineation of the burned area with higher accuracy. Of course, this, for instance, also we have in Italy we have some prescription on the burned area. In the burned area, you cannot do nothing for 10 years. For the next 10 years, you cannot do anything. This was because in the past they just burned the forest or areas in order to change the destination, then they can construct buildings, houses, other things. Then in order to avoid this, the law prescribes that you cannot do nothing in an area interested by a fire. So it's very important to delineate accurately the burned area, because in that area you cannot do anything. Of course, from analyzing the status of the area, you can also estimate if in the area there are some increase in the vegetation. Then you can just do the opposite. Instead of looking for the area where the vegetation was decreased, you can look if in the area, then in particular in the burned area of the previous year or 2 years before, you can monitoring the increase of the vegetation. Then you can have an idea of the recovery of the vegetation in the area. And this is another product more or less similar to the previous one. Okay, this is an example, but I think we can go on. So another interesting product that can be developed, we just, it was developed but not very much verified because there was not strong interest, at least at that time, from the authorities, from the stakeholders, is this one. So an estimation of the burned biomass. This is made on using DTM based on stereoscopic application, also on interferometric method. Then the area, DEM of the area is a DSM of the area is measured before the fires and after the fires. And from the difference, you can estimate the height of the trees, and then you can estimate the biomass burned. That one was something made by with our partners from France. Another thing that we have also developed, but this was of course, the removal of the vegetation can increase the susceptibility of the area to erode, so the surface to the erosion of the surface can increase if the vegetation is removed. And this also was developed applying this model called Rusle, or I don't know if it's in English it's Rasle, but anyway, it's written there. So this is a model commonly used. It has many different terms involved, in particular, for instance, C is the land cover, so the term C is taking into account the type of vegetation in the area, covering the area. Then the other term, LS, is taking into account the slope of the area. Another term takes into account the rainfall of the area, then the amount of rain in the area, and so on. Another one is taking in the K is taking into account the kind of soil, the type of soil. So combining all them all together, then first of all, in this case, we have the vegetation distribution, then the digital elevation model. In this case, we have we tried 3 different vegetation digital elevation model. One was 25 meters, a second one 0.5 meters, and the third one at 5 meters. This is based on the Pleiad images. Then the other term was related to the rainfall. R is just the ratio between the rainfall in 1 month and the average of the rainfall in all the year. Then again, the new one was a map of the soil. Then, of course, this kind of map should be available. So the possibility to compute this in the given area depends on the availability of this map. Then you can come with this soil erosion susceptibility. For instance, the fire was in this case, this example, was in 2009. This is this index computed before the fires. Then after the fires, you can see an increase of the soil erosion susceptibility in some area. Then compared with an image of the same index computed 4 years later, you can see how this risk is reduced due to the new vegetation increased after that time in 4 years. Because the vegetation regrow. Another map or index that we have developed is this so-called damage severity index. Sorry. This index is providing the level of damage pixel by pixel. So is a number going from 0 to 5, and according to the value, 5 means very high damage. So the trees, so everything is completely burned, or 0 means that no problem, there was no effect of the fire. This index called DSE, damage, or DSEI, damage severity index. Okay. So in the case of damage severity index, usually the estimation of the damage is made in the field. So people, experts, they go in the field and then they take note of the burned trees or the vegetation burned, and then using an index called the CBI. This index is based on a certain table with a certain scale that provides information on the level of damage. Then there was developed an index based on satellite images that was called N normalized burn ratio, that is given from that relationship where rho 4 and rho 7 are two channels of a satellite, in particular Landsat in this case. Then measuring that index after the on an image before the fire, acquired before the fire, and one acquired after the fires, they estimate this index, delta NBR, that is provide an indication of the level of the damage in the vegetation. This index was combined with the CBI in order to calibrate sorry, but I will complete now because okay, but I'm very long. Yeah. I'm abusing of your patience. Sorry. So the index was combined with the measurements made on the ground in order, to calibrate the results. This was just an example. The index, this one, on an area, not burned area, that was that area there. This was in a place in the Sardinia, or West Sardinia. This was the index before. This was the index after. So we have a decrease here of that index. That means this area corresponds to the pixel of the burned area. So this index is quite sensitive to the burned area. But that index has several drawbacks, several disadvantages. And then we tried to improve that index, introducing two other indexes. One is called the BSE, Burned Severity Index, that is based on a combination of spectral indices. Another one is the last one that I showed before, is the Damage Severity Index, that is a sort of optimization of the NBR. So the results are given here, but let me go a little bit farther. Okay, let me go to the final part. That means the detection of fires. We can detect the fires using polar orbit satellite as well, geostationary orbit satellite. This is the case of the European MSG, so Meteosat second generation satellite. So as you can see, he has a global view of Europe and Africa and also part of South America. This is another MSG that is moved a little bit on the Indian Ocean, so it's better looking at the Middle East, also some India. So this sensor, this one is providing an image every 15 minutes, also that one. But there is also another one that is providing an image every 5 minutes, but it's just for Europe. Now, we have developed an algorithm that we call it SFIDE, System for Fire Detection, several years ago, that is just, instead of, which is the principle of this, instead of looking at the temperature in the pixel, is looking at the change of the temperature in the pixel. So, exploiting the fact that we have two images at 5 minutes or 50 minutes, one from the other. So more or less after 15 minutes, I can simulate the temperature that the surface should have, because I know the change in the solar condition, illumination condition, and the diurnal behavior of the pixel. Then I can detect any strange behavior with respect to this expected behavior of the temperature. So this improves the sensitivity of the method, because okay, then this is just not folkloristic. something similar. So this is what we are talking about. No, so we are using both of this. This geostationary means that one, polar the other one. So, because one of the drawbacks of the geostationary system is that the resolution, the pixel at our latitude is 4 by 4 kilometers, so we have a pixel of 16 kilometers. But using this method, you can also detect fires that are covering 1 divided 16,000 times the size of the pixel, so that means 0.1 hectares. So this is the system is using 2 channels as usual. This is usual made in the, I will just, of course, again, for instance, if I'm using a polar satellite, in this case of Sardinia, in a day I have 6 images, but in the case of Meteosat, I can have 96 or 96 multiplied by 3, so 200 and so, etc. Let me show a case. Then for any, this is a case of several hotspot or fires detected in Italy in a certain day or a certain year. For any fire, we provide of course, the coordinates of the fires, time, and also the so-called fire radiative power, that is a measurement, provides an idea of the intensity of the fire. And also other parameters like the burning area, the area that is burning, that in this case was, for instance, 0.1700 square meters, and also the fire temperature, that in this case was about 800 Kelvin degrees. Then, of course, in the case of geostationary satellites, we can follow the behavior of the temperature. So we can work on this difference. But if we can follow the behavior of the temperature, we can also, then we can estimate this fire radiative power. And from the radiative power, we can also in some way estimate the burned biomass using some relationship relating the combustion with the biomass. Sensitivity, of course, the question is, okay, how sensitive is the method? So this was just an example. I'm just concluding a few, I think 2 or 3 slides. This is an example of prescribed fires made in Spain. In Spain, they applied this technique of the prescribed fires. Then I tried to see if these small fires, because it was a prescribed fire, was visible from geostationary satellite using our technique. So the area was there in Spain, in the north of Spain. And this was the pixel, the red, you see the red point, this was the pixel extracted by the algorithm from that area using a geostationary image. Okay, here we can see the difference in the delta T, in the change in the temperature due to the fire. This is the pixel with fire with respect to the one without fire. Another case, of course, the sensitivity is also difficult to be done, at least in Italy, because, for instance, there are some fires like this one. This was previous. The fire, that one after the fire. This fire was not present in the list in the report provided to us from the Civil Protection Regional Agency. So you are not able to compare the quality of the results because sometimes they are not in the list, the fire. Mostly if the area was not so relevant, there was not an intervention from them or something like this. So this is just to our website where everything we are producing is available. So if you are interested, the website is there, eocl.psm.1. So you can go, you can look. And this was the project, the PREFER project, in which we did most of these final products. So this is everything. Thank you. Sorry if I'm late, but thank you very much.
Bueno, si no habría ninguna pregunta, después podemos hacer una preguntita específica podría ser. De todas maneras, las demás conferencias, las demás charlas van a estar todas en español y el que nos va a seguir el magíster Nicolás Mari, que casualmente él estuvo con el profesor en Roma haciendo la tesis final del magíster que se hace en CONAI, ¿no es así? Así que él hizo un estudio muy particular sobre la provincia de Córdoba y él pertenece al Instituto Nacional de Tecnología Agropecuaria, el INTA, de la sección de Cruz del Eje. Así que después vamos, más vale de los dos, que se va a aclarar un poquito. Ha sido muy específica la charla del profesor. La manera en que se hacen las alertas en Europa son particulares, a pesar del accidente grande que ha habido en Portugal hace muy poco tiempo. Yo justo estaba en Porto esos días. Y realmente en Bélgica habían hecho una emergencia absoluta en función de las características que había dado la matriz, y así todos los portugueses no lo tuvieron muy en cuenta y se produjo el accidente y le costó la cabeza al ministro de Medio Ambiente de Portugal, ¿no? Así que te invitamos, Nico, le decimos Nicolás, para que continúe él con su disertación y